This is a video on the midpoint and trapezoidal rules. So far you've learned left endpoint approximations and right endpoint approximations. These are going to be two more methods for approximating area under a curve. So the midpoint rule formula. The area using the midpoint rule is equal to the summation of I going from 1 to n of f of x sub I plus f plus x sub I minus 1 over 2 times delta x. So delta x is still the width of each rectangle, just like before. F is still the y, f of this quantity is still the y values, but this is going to be the y value at midpoint of each subinterval. So when we sketch our rectangles, in order to find the area of each rectangle, we're going to take the width times how high or how tall the rectangle is at the midpoint of the subinterval. So it's going to be y values of the midpoint times the width. So here's our first example to kind of see how we apply the midpoint rule. Use the midpoint rule to approximate the area under the curve f of x equals negative x squared plus 5, and above the x-axis on the interval 0, 2, using 5 subintervals. Draw in the actual rectangles that would represent the approximation. So we actually already did this problem with left and right endpoints, so now we're going to find a midpoint approximation. So let's go ahead and we'll sketch first. It's a good place to start. All right, I know that f of 0 is going to be 5, and f of 2 is going to be 1. So my interval goes from 0 to 2. F of 0 is 1, 2, 3, 4, 5. F of 2 is 1. I know that this parabola is concave down because I have negative x squared plus 5, so we can go ahead and sketch our curve. All right. Remember, I left the labeling or the scaling between 0 and 2 blank because we first have to find out the length of each partition. So I'm going to find delta x, or my width of each rectangle, is going to be b minus a over n, or 2 minus 0 over 5, because I have 5 subintervals or 5 rectangles. So my width is going to be 2/5. Let's go ahead and scale by 2/5. So my scaling was a little off. I should have made my goals a little longer. So let's fix that real quick. We'll have 2/5, 6/5, 8/5, and then 2 is 10/5. All right. Now, from here, I need to find the midpoint of each subinterval. So the midpoint, you can find a midpoint on a subinterval by adding the two values and dividing by 2. So like it's just taking the average of the two values. So the midpoint between 0 and 2/5, I'm not going to show work for all of them, but I'll show work for the first one. So like if I wanted to find, oh wait, I made a mistake. So I notice now where my mistake was. I went 2/5, 6/5, 8/5, 2. We have to go ahead and fix that. So it should have been 2/5, 4/5, 8/5, and 2. So let's go ahead and fix that. moving a little too fast. And here we go. So I got 2 fifths, 4 fifths, 8 fifths, or 6 fifths, wow. 6 fifths, 8 fifths, and 2. And now I actually have 1, 2, 3, 4, 5 subintervals. I apologize for that. So now the midpoint, we have to now find the midpoint of each rectangle. So the midpoint between 0 and 2 fifths is 1 fifth, because if I added these together and divided by 2, I would get 1 fifth. 0 plus 2 fifths divided by 2 is 1 fifth. I'm going to do this and find the midpoints in a different color just so we can kind of keep track. All right, the midpoint between 2 fifths and 4 fifths would be 3 fifths. Zoom in a little bit. All right, the midpoint between 4 fifths and 6 fifths would be 5 fifths or 1. The midpoint between 6 fifths and 8 fifths would be 7 fifths. And the midpoint between 8 fifths and 2 would be 9 fifths. All right. Now, when we draw our rectangles, what I am going to do is take each midpoint up to the curve. All right. Now, my midpoint is on the curve. I'm now going to take each side of my rectangle out to the end of the subinterval. So the first subinterval goes from 0 to 2 fifths. So my rectangle goes from 0 to 2 fifths through the midpoint. And now I'm going to come back down. My next midpoint is 3 fifths. So I'm going to take 3 fifths up to the curve, because whatever type of approximation it is, you take that point up to the curve. Here is where here's f of 3 fifths. Now what I can do is take my rectangle to the left endpoint of the subinterval and the right endpoint of the subinterval and come back down. Next, I'm going to take 1 up to the curve. Plot f of 1 and take the rectangle to the left endpoint of the subinterval and the right endpoint. Let's take 7 fifths up to our curve, touch the curve at the midpoint, extend the rectangle to the beginning and end of the subinterval, and then let's take 9 fifths up to the curve and extend our rectangle to the beginning and end of our subinterval. Now, the midpoint rule states that we're going to take all of our widths times the function evaluated at the midpoints, because our height here is the y value at the midpoint. So these dashed lines represent the height of each rectangle, the y value at the midpoint. So here I have f of 1 fifth. Here we have f of 2 fifths. That should be 3 fifths. Apologize. Here I have f of 1. Here I have f of 7 fifths. And here I have f of 9 fifths. Now, let's find the area of each rectangle. Our first rectangle has a width of 2 fifths, because we're going from 0 to 2 fifths. So I have our area is 2 fifths times the height of the first rectangle is f of 1 fifth. The second rectangle has a width of 2 fifths times a height of f of 3 fifths. My third rectangle has a width of 2 fifths times a height of 1, or of f of 1. Sorry, f of 1, sorry. All right, the last rectangle has a, or the fourth rectangle has a width of 2/5 times f of 7/5 would be our height. And then last, I'm going to have plus 2/5 times our last height is f of 9/5. All right, so oops, I didn't mean to be off the screen here. Let's factor out a 2/5. So I'm going to have our area is 2/5 times f of 1/5 plus f of 3/5 plus f of 1 plus f of 7/5 plus f of 9/5. All right, I'm happy with this expression right here. But then what we can do is if I actually plug in the values of 1/5, 3/5, 1, 7/5, and 9/5 into the original function, I already did this with the calculator. We're going to get 124 over 25 plus 116 over 25 plus 100 over 25 plus 76 over 25 plus 44 over 25. I just evaluated these in a calculator. I plugged in each one of my x values into f of x, and I got my values. Then from there, what we can do is add them up together. I'm going to have 2/5 times 460 over 25. Then what I can do is do some cross canceling. Divide by 5, get 1, divide by 5, I'll have 92, multiply straight across, and I get 184 over 25. All right, this is my area approximation using the midpoint rule. So to summarize, we first sketched our curve, found the length of each subinterval, which was 2/5, identified the midpoint of each subinterval, sketched the rectangles by drawing a dashed line from the midpoint up to the curve. The rectangle should start and end at the endpoints of the subinterval. From here, find the area of each rectangle by taking the width of the rectangle, which here was 2/5, times the height, the function evaluated at that x value, and then we simplified. So I am happy if you can get, I'm good. I'm looking for you being able to get all the way to this step, because the rest is just algebra and using a calculator. So I'm looking for you being able to write this expression for a midpoint approximation. What I'm going to have you do right now is go ahead and pause the video. All right, and I'm going to have you do you try. So use the midpoint rule to approximate the area under f of x equals 8 over the quantity x squared plus 1 and above the x-axis on the interval 2, 6 using 4 rectangles of equal widths. So go ahead and pause the video right now, and I want you to try it, and then you can check your work with mine when you are finished. All right, so let's go ahead and get started. Okay, so let's start by graphing our function. We're on the interval from 2 to 6. So f of 2 is 8 over 5. And f of 6 is 8 over 37. All right, so 8 over 5 is 1 3/5. So we're going to be at approximately 1.6. So I'm going to take my curve up to 1 and 2. So f of 2 is 1.6, so I got to estimate. And f of 6 is 8 over 37, so that's about, it's close to 1/4, because 9 over 36 would be 1/4. So 8 over 37 would be kind of close to 1/4. All right, let's go ahead and sketch our curve. All right, we want 4 subintervals. So our delta x is b minus a over n, or 6 minus 2 over 4. So each rectangle should have width 1. So I'm going to have 3, 4, and 5. So then now I can see I have 1, 2, 3, 4 subintervals. All right, next I need to identify the midpoint of each subinterval. So between 2 and 3 we have 2.5 or 5/2. Between 3 and 4 I have 3.5 or 7/2. Between 4 and 5 I have 4.5 or 9/2. And between 5 and 6 I have 5.5 or 11/2. Now, let's take each midpoint up to the curve. Sketch the rectangle by starting and finishing the rectangle at the endpoints of the subinterval. Let's take 7/2 up. Let's take 9/2 up. Let's take 11/2 up to the curve. So I drew this kind of small, but you can always draw yours bigger too, so that you have a little bit more room to sketch the rectangles. So now let's go ahead and write an expression for our area. Our area will equal, each width this time is 1, because each rectangle or each subinterval has a length of 1. So I'm going to have 1 times f of 5/2. The height here, the y value is f of 5/2, plus 1 times f of 7/2, plus 1 times f of 9/2, plus 1 times f of 11/2. All right, and now from here we can factor out 1, because that's our width. So 1 times f of 5/2 plus f of 7/2 plus f of 9/2 plus f of 11/2. All right, and then I just use a calculator, but I plugged in 5/2 into 8 over x squared plus 1, and I got 32 over 29 plus 32 over 53 plus 32 over 85 plus 32 over 125. When I add each of these fractions together using a calculator, because that will be a messy common denominator, I get 2.340. Notice I use 3 decimal places because you have to round to 3 places on the AP exam. All right, so this concludes the midpoint rule. You find the width of each rectangle and then evaluate the function, the midpoint, to find the height of each rectangle. You can work it out from there. So let's go ahead and move on to trapezoidal sums and the trapezoidal rule. So trapezoidal sums and the trapezoidal rule. So far you have 3 methods for approximating area. There's left endpoints, right endpoints, and midpoints. We can also use trapezoids to approximate area under a curve as well. So we need to throw it back to geometry real quick with the area of a trapezoid formula. So the area of a trapezoid is 1/2 base 1 plus base 2 times the height. So our height is the distance between base 1 and base 2. And then the bases are always parallel. So it's the 2 sides of the trapezoid that are parallel to each other. So you see base 1 is parallel to base 2. Now I have the trapezoid drawn here like you see it in geometry. I'm going to draw it now how you'll see it graphically when we use a trapezoidal approximation. So it might look something like this when we do our trapezoidal approximation. So notice I rotated the trapezoid. So maybe my height will actually be down here. And then I'm going to have base 1 and base 2. All right, so notice I just rotated the trapezoid. So you'd still use the same formula, just the height is going to be sideways this time, because the bases are always the two sides that are parallel. Okay, so you're going to have to recognize that bases are parallel. When you see that on the graph in a second, you have to recognize the same thing. But now, let's take it one more step. How it's actually going to be when we do it graphically is it's going to look something like this. My height is actually going to be my delta x, because it's going to be the distance between each endpoint of the subinterval. All right, and then my base 1 is going to be the function evaluated at whatever this point is. We can call this maybe x sub I minus 1. So, because like this would be our first x value, this would be our second x value. So maybe this is f of x sub I minus 1. So I would be evaluating the function at this point, and then I'd find the height over here by evaluating the function at this point, and then I can plug them into the formula. So this is just a little preview of what it's going to look like. So let's go ahead and actually do an example with the trapezoidal rule. Use the trapezoidal rule to approximate the area under f of x equals the square root of x minus 1 and above the axis on the interval 1, 6. Right? And then I should have said using 5 subintervals. All right, so let's go ahead and do the same thing with graphing first. So I have a sketch. Let's evaluate the function at the left endpoint. So f of 1 is going to be 0, because if I plug in 1 and have 1 minus 1 or 0, square root of 0 is 0, and f of 6 is going to be the square root of 6 minus 1, which is the square root of 5, which is approximately 2.23. All right, so let's go start at 1. All right, our last point is 6. All right, so f of 1 is 0. Since I'm only going up to 2.23, I'm just going to scale by 1s and go up to 3. So 1, 2, 3. So f of 6 is square root of 5, so I have to estimate where that is, about 2.2. Let's sketch our square root curve. All right, next, I want 5 subintervals, so let's go ahead and do that. So our delta x is going to be 6 minus 1 over 5, which is just 1. So now let's scale by 1s. Okay, now from here, on each subinterval, I'm going to have to sketch a trapezoid if I can. So sometimes you're not able to sketch a trapezoid. It ends up being a triangle when the height of the height at an endpoint is 0. So I'm going to start here. First, I'm going to bring each of my endpoints up to the curve. All right, now to make trapezoids here, I am going to just connect the y values at the endpoints. So I might have to hit this a little bit. All right, so this is going to be kind of hard to see. So if I first label each one of my endpoints, All right, I am going to have to connect each one of these endpoints. Now, it's hard to see, but all right. Now, I'm gonna zoom in for a second. All right, so each one of these figures on each subinterval is a trapezoid. Now, it's really kind of hard to see the way I drew it right now, but there's just a little bit of area under the curve that's missing here. So we're missing some area, I'm missing some area, I'm missing some area, I'm missing some area, and I'm missing some area. So each one of these is technically a trapezoid, because notice the sides of each subinterval are going to, the sides of each on the figure in each subinterval are parallel. All right, and my height of each subinterval is going to be the length, or the delta x. So now what I can then do is for each subinterval, I can write an expression for the area of the trapezoid. So let's go ahead and do that. So now for the first trapezoid here, well, it's actually not a trapezoid, it's a triangle, but I can still use the trapezoidal rule. I'm going to take 1/2. Now, base 1 is the height on the left side, so I'm going to have f of 1. Base 2 is going to be the height on the right side, plus f of 2 times the height of the trapezoid is going to be 1, because each of my subintervals is the height of the trapezoid. Like, all right. So now my next trapezoid is, now I'm looking at this trapezoid right here. I need you to see the trapezoid. So I just outlined it in blue. So I'm looking at this trapezoid. All right. So the height, or the height of, or base 1 of the trapezoid is going to be f of 2. Base 2 is going to be f of 3. My height is going to be 1. So I'm going to have plus 1/2 times f of 2 plus f of 3 times my height of 1. Fix this real quick. Now, I am on the third trapezoid, so I'm on this trapezoid now here that I just highlighted. All right, so the trapezoid that's on the subinterval from 3 to 4. So base 1 is going to be f of 3, because my height here is f of 3. Base 2 is going to be f of 4. To find the area of the trapezoid, it's 1/2 base 1 times base 2 plus base 2 times the height. So my next trapezoid is going to be 1/2 f of 3 plus f of 4 times 1, my delta x. I'm on the fourth trapezoid now. All right, so it should be look parallel. All right, so now let's go ahead and do that. So I'm going to have for the fourth trapezoid plus 1/2 f of 4 plus f of 5 times 1, because my height is 1 still. And the last trapezoid, 1/2 times f of 5 plus f of 6 times my height of 1. Now, I need you guys to look through and notice the pattern that each term that's separated by addition here, we can factor out a 1/2 and a 1. So I'm actually going to factor out a 1/2 and a 1. So if I factor out a 1/2, let's move down here so I have a little more room. So let's factor out a 1/2 and the 1. All right, So if I factor out a 1/2 and a 1, I'm going to have f of 1 plus f of 2. Here I factored out a 1/2 and a 1, so I'm going to have plus f of 2 plus f of 3. Here factor out a 1/2 and a 1, so plus f of 3 plus f of 4. Right here factor out a 1/2 and a 1 plus f of 4 plus f of 5. And here factor a 1 out, f out of 1/2 and a 1 plus f of 5 plus f of 6. All right. Now what I can do is I notice I have some terms I can combine in here. I'm sorry that I'm running out of paper. I wish I could have expanded this all the way out, but I ran out of paper. So let's go ahead and I see that f of 1 plus f of 2 is going to be 2f of 2. And f of 3 plus f of 3 is 2f of 3, 2f of 4, 2f of 5. So I'm going to have 1/2 times f of 1 plus 2f of 2 plus 2f of 3 plus 2f of 4 plus 2f of 5 plus f of 6, because I only had one f of 6. All right. Now, we got to remember that our original function was f of x equals the square root of x minus 1. So if I plug in 1, f of 1 is 0. If I plug in 2, I'm going to have plus 2 times 1, because f of 2 is 1, plus 2 times the square root of 2, because if I plug in 3, I'm going to have the square root of 2, plus 2 times square root of 3, plus 2 times 2, because if I plug in 5, I'm going to get the square root of 4, which is 2, plus the square root of 5 if I plug in 6. All right. And when I put this in a calculator, I'm going to end up with approximately 7.2. All right. This is the intro to the trapezoidal rule. We'll be working on it in class next week as well. So please let me know if you have any questions. Thanks.